This week we are going to take a tour of ocean basins. So the idea here is to take some of the information that we learned from plate tectonics and also look forward to some of what we're going to discuss when we talk about ocean sediments and other topics over the course of the semester. And we're going to use chapter 4 as a sort of a vehicle to do that. And the best way to do it is to take a trip across the Atlantic Ocean and then take a trip across the Pacific Ocean. And we can see some of the features that are present. We can see similarities and differences. And in class this week, we will actually draw these profiles and talk about what we find. So the purpose of this slide presentation is just to highlight a few of those features. And we will actually begin by talking about where this information comes from. So some of our best and earliest information on the depth of the ocean floor comes from soundings, which is when you send a sound wave down and it bounces back up, you see how much time it takes to get back to the ship, and that tells you the depth of the water. And so this allows us to develop a picture of the ocean floor. There are also techniques using satellites, and this image from the book kind of shows you how that works. But the bottom line is we end up with images that look like this. It takes a lot of data to produce a map like this, but it also provides us with an opportunity to see many, many features and their relationships to each other. So what we're going to do is we're going to start on the upper left here on the east coast of the United States, and then we're going to work our way across the ocean basin until we get to Africa. That's what we'll do in class. What we'll do in here is just talk about a couple of the key features that we're going to take a look at. And we're going to start over here at the continental margin. And so the continental margin includes three parts. It includes the continental shelf, the continental slope, and the continental rise. Now, one thing I should point out, that this image that we're looking at has a lot of what we call vertical exaggeration, which means that the vertical scale, the depth, is very much stretched out compared to the horizontal scale going across. And in fact, they've labeled it. You can see that the depth here goes from 0 down to 5 in terms of kilometers, or if we look on the right-hand side, 0 down to 3 miles till we get to the deep ocean floor. If you look across the top, you'll notice it goes 100, 200, 300. You can see that scale on the top is very different from the scale on the side. If you want to see what this actually looks like with no vertical exaggeration, they've provided an image at the bottom here, a little drawing, and you can see that the continental slope and rise are actually quite gentle. They're not nearly as steep as they look on here. So the formation of this continental margin actually goes back to the divergent margins that we talked about with plate tectonics last week. If we looked underneath here, what we would see is a series of faulted blocks of continental type crust that would stair step from left to right, kind of down till they merge with the deep ocean floor. That material is then covered with sediment over time. That was originally half of the Rift Valley as the plates began to pull apart. And then as it pulls far enough away, it's no longer at the plate boundary. It becomes what we refer to sometimes as a passive margin. But it ends up getting covered with a whole bunch of sediment washing off the continent. And that's what creates the continental shelf. The continental shelf is partly underwater and partly on land. And really, technically, we only call the part underwater as the continental shelf. But sea level rises and falls. And when sea level is at its lowest, as it was at the peak of the last ice age, the water level is all the way out here near the shelf break. And when sea level rises quite a bit, if the ice caps melt, then much more of this would be flooded, and so you'd have a much wider continental shelf. At the edge of the continental shelf is what we call the continental slope. You can see they have a little pointer here that says shelf break. It's roughly 460 feet deep. There is a very steep section that we refer to as the continental slope, and then as we move away from the continental slope, we get what's called the continental rise. Now this whole area is covered, this whole section is covered with sediments that are washing off the continents. If you're on the continental shelf, you're looking at sediments like sand and material coming off of rivers, and some clay, and also on the shelf you'll find some sediments produced by living organisms. As we get out into the continental slope and rise, things change a little bit. This shows a portion of the continental shelf off of the east coast of the United States. Up here we have New York City. This is Long Island, and the Hudson River comes out here. And you can see they're located on the continental shelf. The area that's shaded in red to yellow to green to blue is the continental slope and the continental rise. And that is being built up with sediment that's washing off the continent. And a lot of that sediment moves through what we call turbidity currents. We're well below where the waves are able to do any damage or move sediment around. We're in what you might think of as quiet water if you're underwater. But it turns out that if that water is mixed with sediment, we get something called a turbidity current. And turbidity currents are essentially muddy water or sandy water because they're more dense than the surrounding clean water. The turbidity currents can move along the bottom of the ocean floor, and you can see in the bottom right-hand side, it's almost like a little river coming off of there. So this turbidity current is probably associated with a river on land, bringing a lot of sediment out. The one in the top right is probably associated with an underwater landslide. Either way, these turbidity currents move large quantities of sediment from the continental shelf across the continental slope and deposit them on the continental rise. So that's how the sediment moves around there. The next feature we want to take a look at as we go across the ocean is the mid-ocean ridge. And the mid-ocean ridge we've talked about, again, divergent margin. You can see where the mid-ocean ridges are located. They're colored in red on this map. And here is the mid-ocean ridge at the center of the Atlantic Ocean. The mid-ocean ridge is a place where the plates are pulling apart. So this is a divergent margin. And at the center of the mid-ocean ridge is a rift. So there are blocks of rock that are kind of dropping down in to fill in that gap as these plates pull apart. And there's also molten rock rising up from below to fill in that gap as well. This is kind of a high resolution map showing the shape of the ocean floor at the crest of the mid-ocean ridge, and you can see the rift very clearly defined right in the middle here. If we look at the rocks of the mid-ocean ridge, you'll notice as you move away from the center on this drawing, they're very, very bumpy, and this is what it looks like when we look at sonar from the side. One of the things that's striking about this, you can see the rift here in the middle, or actually the rift is a little off to the right, I should say. As this moves away from the rift, you'll notice that there's material filling in the low spots between these peaks. And that is sediment slowly filling in over many, many years as this becomes inactive when it moves away from the rift. So the rift in this case would be off on the right-hand side, and we're moving into this area kind of off the side of the mid-ocean ridge. And it's important to recognize the kind of the slow covering of sediment that occurs as these rocks move away from the mid-ocean ridge. And we'll come back to that in a moment. If we look at the mid-ocean ridge itself, down in the rift, we actually find underwater volcanoes, and we find underwater geysers that are referred to as black smokers. And what's going on here, this is what they look like. You can see it, this dark material coming out of the top. That's why they call them black smokers. But what's happening is seawater is seeping into the ocean crust. It encounters or gets close to the molten rock that heats up the water. The water is then able to dissolve minerals, and it comes back out through these underwater geysers with a lot of dissolved mineral material in it. However, the water at the bottom of the ocean is about 2 degrees centigrade. It's just above freezing. So when the hot water meets the cold water, the water cools very quickly. It can no longer hold all that dissolved material, and so a precipitate forms, and that is what we see as this black, dark material coming out of the top. And it precipitates directly onto the top of this little chimney. And what will happen to these chimneys over time is they'll grow taller and taller, and they'll end up plugging themselves up or getting too tall to stand and tip over, and the process begins again. So this is what happens at the mid-ocean ridge. The other place where we could go see the mid-ocean ridge is here. This is Iceland. That's a place where the activity at the mid-ocean ridge has been high enough to build the mid-ocean ridge up to and above the surface of the ocean. And so if you go to Iceland, you can actually stand with 1 foot on the North American plate and 1 foot on the European plate, and they're very slowly pulling apart and opening up Iceland. So there's actually a rift that runs right down the middle of Iceland. Now, the other feature that's kind of interesting to see, and let's go back to this. Remember, these are the rocks that are moving away from the mid-ocean ridge. We can see they're already getting covered with sediment. And over time, that sediment cover can build up and completely bury those little peaks. So the oldest parts of the ocean floor look like this. You can see the original surface of that crust that formed at the mid-ocean ridge is the rough surface kind of at the bottom of this profile. And then the top part that looks very, very flat is the top of the sediment that is slowly filled in the low spots and then covered over the peaks. This feature is what we refer to as the abyssal plain. It is a flat area. You can see on either side of the mid-ocean ridge. I've zoomed in on that map from the textbook. You can see the flat area here on the east side of the Atlantic Ocean. There's another flat area over here and over here on the west side of the Atlantic Ocean basin. They name these separate abyssal plains, but altogether, these are areas that over time have been filled in. And if we use the right kind of sonar to look into the sediments at the bottom of the ocean floor, we can see kind of that original oceanic crust, and it's covering, in some places, very thick covering of sediment that then creates the abyssal plain. This abyssal plain is often marked by features that we call seamounts. And seamounts are simply very active places from the mid-ocean ridge that were active enough to build a large volcano. And very often these large volcanoes will be colonized by living organisms, so they will kind of build up around here and create a reef. Modern coral reefs are an example of this kind of activity. And then when that moves away from the mid-ocean ridge, it sinks below the surface. But if it's active enough, you can see we still have one peak here. This would be a seamount that still pokes above the abyssal plain simply because the igneous activity built it up to the point that it was quite tall. So those are the primary features that we will see in the Atlantic Ocean basin.